Vector graphics allow us to create much smoother rotation than's possible with bitmap sprites. So let's see how it's done in our Space Commander game. Hi and welcome to Bytes and Bits. In this video, we're going to make a start at coding Space Commander using our Fantasy Console development system TIC80. Now, if you've never used TIC80 before, it's a complete games coding system that makes learning to write your own computer programs loads of fun. And I've produced a few other video series taking you through from the very beginnings of coding right through to making your own games. So please do check those out on the rest of my channel, and I'll put some links up in the right-hand corner there. Now, as you've seen from the introduction, we're going to be tackling the vector graphics coding in this episode. So we'll be looking at how we can define our images, encode that data, draw them on the screen, and then getting as far as being able to move, rotate, and scale our vector graphic elements. Now, don't forget that you can download all of the code for this episode by visiting the main project page on my website, and I'll put some links in the description down below. And if you want to follow this full series and have a go at coding Space Commander by yourself, then make sure you subscribe to my channel and click that notification bell to make sure you don't miss any of the episodes. So, let's get straight into the coding and work out what vector graphics are and how we can apply them to our game. So one of the main reasons why vector graphics will help us is to overcome the difficulty in smoothly rotating these bitmap sprites. So if we have a look at one of the retro games, and this one is Galaxians, we can see that as the aliens start to dive, they do this rotation effect as they take off. And that's created by actually drawing a number of different frames for each bit of the rotation of the alien. And if we have a look at the sprite sheet, so the actual graphics which are used in this game, you can see that they've had to draw the alien, or each alien, in a number of different rotations. And those then are used in the animation to produce that rotation effect. In this instance, we can see that each alien is drawn in 6 positions to do a 90-degree rotation. And we can then use flipping and mirroring and rotating of these bitmap graphics to fill in the other 360 degrees. But even with this number of images, we're still getting about a 15-degree jump per sprite change. And that doesn't give us this totally smooth effect that we're after. And it also means then that as the aliens are going to be firing their missiles and so on, it's not going to quite come out from the same direction that the alien is pointing. Vector graphics then allow us to overcome this limitation by defining our game characters as a series of lines. We can then define the endpoints of each of these lines and then draw those, and as we rotate those points around an origin, we will actually get a very smooth rotation. So let's have a look at how that's built up. So our image is going to be a series of lines, and to define those we need to define the endpoints of each line. We'll start by defining a local origin for this image. So this is going to be in effect the center or the insertion point of this individual image. And then each of our points will be defined relative to this local origin. And as we plot subsequent points, we then need to specify whether this point is a new line starting or whether it's a continuation of the previous line where we need to draw a line then between this point and the previous point. So in the animation on screen, the first point we plotted was a new line. The second point we plotted was not a new line, so it simply draws a stroke between the previous point and this second point. And we can then continue round the rest of the outline of our enemy ship until we get back to our starting point. And each of these points, of course, are continuations of the existing line. With that complete, we can use this ability to specify a new line starting point to fill in some extra details and perhaps add a little cockpit for the enemy pilot. So again, the first point will be a new line, and then the subsequent points will be continuations of that line so that strokes get drawn in between them. And at that point, we've finished drawing our enemy ship. So that gives us the basic algorithm that we're going to use. But we now need to encode this data as a series of instructions that our software can interpret to reproduce this graphic. To do this, we can use an array or table in Lua to hold a number of elements, and each of those elements will contain the information required for that particular point. And each point then will have to have its x and y coordinates, and again that's relative to our local origin, whether this is the start of a new line, and then the colour that we want to connect it to the previous point with. So now that we know what to do, let's jump into TIC80 and see if we can code this vector drawing algorithm. So this is the raw vector drawing code that we're going to be building up over this lesson. To begin with then, we're in TIC80. We're defining a few variables at the beginning here. So this is going to be modeling one of our enemy ships. So we're going to create a ship variable, which is going to use one of these Lua tables, denoted by these curly braces here. And that in effect is our way of building up a little object. So inside that Lua table, we can in effect create little attributes within that, which themselves are variables. And here we're creating an attribute called position, and that itself is a little table, or as we're referring to them here, little objects, which has an X attribute and a Y attribute. So that in effect gives us a screen position in this format where we are using another little Lua table. Now, if this isn't familiar with you, or if you're not too familiar with the idea of objects and so on, do have a look at my Space Invaders and Asteroids courses, which will take you through how we're implementing this in this Lua language inside TIC80. And as I say, this isn't a full object-oriented system, but it does let us use these. In effect, if you're familiar with Python, these would be termed dictionaries within Python. But it does let us then create a variable which has got other sub-variables buried inside it. And that just makes it easy to transfer it around. But as I say, this is really just to give us the basis for a ship. So we have a ship which has an attribute called position, which itself is made up of x and y coordinates, a velocity, which will come in more when we go to do the movements around in our game, which has got a magnitude and an angle. And then we're going to use something called scale here as well, which we'll be using a bit later on in this lesson. So that just gives us a ship which is defined. So we have defined the position of the ship, and in effect this angle defines what orientation it is in. But then in our main tick function, so this is in effect our update routine, which gets called 60 times per second. So we're going to clear the screen, and we're then going to use this little helper function called draw object. And we're really going to say we're going to draw object, we're going to tell it what type of object we want to create, which is a ship number 1, and where we want that put on the screen. So we're just simply going to give it the ship position. So obviously this draw object, this little bit of code here, is the one which actually does our vector drawing. So we're coming in here with the object type as our input parameters and our origin, so that's where we're going to draw it. So I'm using a little helper function here. So this object type, as we saw, that is going to be a reference to the particular shape of ship that we want to draw. So instead of embedding all of that point information inside our actual ship object, we're just going to use a reference, and a bit further down we're going to then pull that particular shape's points out of a data structure. So we have our object type coming in, and at this first line here we are then calling this second helper function, this getObjectShape. We're telling it which particular object we want, and that will return us back this array of points. So let's have a look at that function for now. So here we have our getObjectShape. And we can see here that we come in with our object type. We're going to create a local table here, which is going to contain all of the points required for this particular object type. And then we just simply fill it up. So you can see here we're reinitializing our variable. Again, eventually this will have all of the different enemy ship shapes stored within it, and it will select the right one and return that back to you. But at the moment we're just simply using one shape. And you can see we are simply creating, if I just scroll along here a wee bit. So you can see that this block here is the definition for this point. So we have our x coordinate and our y coordinate, and again these are relative to our local origin, whether this is the start of a new line or not, and then what color we're going to draw this line in. And again, if this is a new line true, then obviously that color is not actually relevant. It won't draw a line until we get to the next point. But you can see here, this is how we've done it. And this is exactly the same as you saw in the animation. Again, we're using curly braces here because these are Lua tables, and that's just the way that Lua works. So we can see here we have our first point in the -5, -5 coordinate. Then we have 0, -4, and so on. And these are all then one line until we get down to the second true section here, and that of course then is drawing the cockpit for the enemy pilot in a yellow color here. So these colors actually should show you as well. If we go across to our Sprite Editor, which is on this little icon here, you can see colors down the bottom. So again, this is color 0, and then 1, 2, 3, all the way up to 7, 8, and then all the way up to 15 here. So our color 14 then is our yellow. So we can see that we now have all of our points defined here. We are using this table.insert method. So that says insert into a table. We then tell it which table we want to insert this into, and then what we want to insert. So in effect, this first point goes into the first element in our table, then the second point goes in as the second element in our table, and so on. Then once we've built up this table full of all of the points that describe our enemy ship, we simply then return that back as the return function, the return parameter for this function. So back up here, you can see then that our local variable object shape will receive that data structure. And at that point, we can now go through and draw this image. Once we've got our shape definition, the actual rendering of the lines is fairly straightforward. So we've got our object shape variable now contains this array of point objects. So we're going to create two local variables. One is going to hold the information about the current point, and one is going to hold the information about the last point that we drew. So we're then going to iterate through each of the elements in our object shape variable. So remember, that is the list of the points that make up our image. So this little construct here, this iPairs construct, does that. So it will generate inside our loop, we will have a variable called index, which will tell us which element we're looking at, or the numerical index of that element, and then the actual element itself, which we're going to save in this little local variable point. So for each point, we simply need to move it to the correct position on the screen. Now, everywhere in this game where we are referencing coordinates and angles, I'm going to use the standard mathematical layout. So that means that our x-axis is horizontally to the right, and our y-axis is vertically upwards. Again, that differs from our screen where the y-axis is the other way round. And as well, that any angles we do, I'm going to take horizontally to the right as being 0 degrees, and any positive angles go in an anti-clockwise direction from that. I'll discuss a bit more in the next lesson when we talk about the world coordinates and mapping those, as to why I've chosen that particular way round. And really the upshot is that I am familiar with the mathematical notation, so it makes it's easier for me to think of it in those terms than trying to match in with screen coordinates and so on. But say more about that in the next episode. But really the upshot of that is that the screen position of this point, so its x coordinate, will simply add on the insertion points. Remember we talked about the local origin for our image, and that was either the center of the image, or you can think of it then as the insertion point. So that comes in as this origin parameter that's sent in where we want it on the screen, and we're simply then going to add that x value onto our point's x value, and that will give us the screen coordinates then for that x value. The y value then, we simply need to invert or negate the y value from our image, okay, and then add that on to the y value for our origin. So basically, if we have a positive value, so say we are at +5 pixels in our point array, then we simply need to take that away in effect from our screen Y position so that it sits above our center point rather than below our center point. So that then gives us our point X and point Y will now be screen coordinates for this point. We then simply need to do two things. Either this is a brand new line, and if it's a brand new line, we don't actually do anything other than update our last point variable. So our last point variable then becomes equal to the currently processing point. So the next time through this loop, we of course will have our last point being the last point that we met. If it's not a new line, then we actually have to draw a line. So we simply draw a line from the last point, okay, specifying it in those two coordinates there, to the new point, and then we simply draw it in the correct color. So remember our point object has a color built into it. So remember that's from down here. We have our colors inside our point object. So we'll simply draw that line in that color, and then after that we then simply update our last point information. So again, the next time through this loop, the next iteration, our last point variable is pointing to the last point that we processed, and that is all we have to do. So this little line of code, this little loop here, is all that we need to do to actually draw this and make sure that we draw new lines in the correct color. So let's just run that and see what happens. And there we have our alien ship drawn in the center of the screen. And you can see we've got the green outline and then the yellow cockpit. Now, of course, at the moment, we're drawing it quite small, and this will actually be the correct size for use in the game itself. But it'd be quite handy if, especially for testing purposes, we could actually make that just a little bit bigger and use some sort of scaling factor on it so we can see our individual lines to make sure that they are actually drawing correctly. So let's come back into our code and let's see if we can do that. So if we go back up to the top of our listing, you can see I've already added a scale attribute into my ship object. So down here, what we can do is before we draw our ship, we can actually alter the scale of it. So I'm just going to copy a bit of code across in here, just bear with me a second. So what I'm going to do, I'm going to use the up and down arrow buttons on our keyboard to adjust the scale. And you can see here, all I'm doing is if I get an up arrow button, which is button 0, then I'm just going to add 0.1 onto the ship scale value. Okay, so remember ship scale is the scale attribute in our ship variable, and I'm just incrementing it by 0.1. And again, with our vector graphics, again, we have this ability to very smoothly scale our objects. So if we're looking at bitmap graphics and the sprite system inside TIC80, we can use integer scaling values, so we can make it twice as big, 3 times as big, 4 times as big, and that just simply allows it to, in effect, instead of drawing 1 pixel, it draws 2 or a block of 4 pixels, 2 by 2, to scale it to twice the size and so on. But again, with our vector graphics, our scaling is very, very smooth. So up arrow key will increment it by 0.1, down arrow key will take 0.1 away from it. So now we've set the scale, we need to pass that into our drawing function. So we will do ship.scale and pass that value in. So inside our draw object, we will need to receive that parameter. So we'll just receive it as a local variable called scale. And then to do the scaling, once we have our actual point, we simply just need to, if I just do scaling in here, we just simply need to multiply the position of that point by the scale factor. So again, this is before we move it to the screen position. So again, at this point here, our point X and point Y are relative to our local origin. Again, the insertion point of our image. So if we just simply multiply the coordinates of X and Y by our scale factor, that will then just make our shape that much bigger. Then we go on and continue with then moving that local centered points onto the actual screen in the correct position and then draw the shape. So that should now let us do that. So let me just save that and run that and we'll see what happens. So now if I use my up arrow, you can see that we are scaling our shape, and we can see there each of the individual lines that we have used to draw the shape. And then of course if I use my down arrow key, we can then scale it and make it really small. And again, I haven't put any error checking if we go below 0. So bigger and smaller. So we can now draw our shape and we can scale our shape and we can place it on the position of the screen where we need it to be. So let's start looking at how we can rotate the shape. So let's come back into our code and have a look at that. First, we need to do a bit of mathematics revision. So let's consider our normal X and Y coordinate system, where we have our positive X axis extending horizontally to the right and the positive Y axis extending vertically upwards. And here, angles are measured from the positive X axis, with positive angles being anti-clockwise from this. And again, this is the normal mathematical view of our two-dimensional space. So if we consider our point at coordinates x1, y1, we want to rotate this using the origin as the center point of rotation. And we want to rotate it by an angle theta, which will get us to new coordinates x2, y2. Now, we don't need to go into the mathematics of how we work this out. We just need to get hold of an equation that lets us calculate the new coordinates. And if you're not familiar with trigonometry, don't worry about what sine and cosine are. Just accept that these are mathematical functions which are built into almost every computer language, including Lua. So our equations to rotate this point around the origin are that the new x-coordinate x2 is equal to the original x-coordinate times the cosine of our angle theta minus our original y-coordinate y1 times the sine of theta. And our new y-coordinate, so y2, is equal to y1 times the cosine of theta plus x1 times the sine of theta. And again, all of these rotations are based around our central origin point. Coming back to our code then, if we look at our ship object definition, we already have our velocity, and we have inside that then this angle attribute, which at the moment is set to 0. And again, that is in effect the direction in which our ship should be pointing. So inside our TIC function then, we're already doing a bigger and smaller with our scaling. We could then start to play with this angle. So if I just paste in some code there, and again, that's all just looking at using our left and right arrow buttons. So if we press the left arrow button, we will then increase the angle of our ship. So remember, anti-clockwise is a positive angle shift. And then if we use the right arrow button, that will decrease the angle of our ship. When we come to draw our object, so we're now passing in the shape we want to use, the position that our ship should have on the screen, and its scale. We also then want to add in our ship dot velocity dot angle, and of course that will then pick up the angle attribute from our ship's velocity, and that needs to be passed in then to our draw object function. And again, I've already put that code into our draw object. So in a draw object, you can see we're getting the object reference, we're getting the origin, so where on the screen we want this to be. We're now receiving an angle and then the scale as before. So inside our draw object, what we're going to have to do, again, we need to iterate through each of our points. So everything else is the same here. I've created a new local variable called rotated point. So each individual point we're going to have to take its original position and then rotate it by the correct angle. So we can see inside our loop we have our rotated point, and we're then using another helper function called rotate point. And that rotate point, then we need the center of rotation. So at the moment when we're just simply drawing these objects, we know that they each are all centered around their own origin. So remember, that's whenever we define the points, and we then eventually move those off to the correct position on the screen. So at the moment we will be, all of the points in our points array are already centered around a 0, 0 origin. So but we need to pass that in, because eventually this rotate point function, we'll be using that when we come to rotate things within our actual real world. So that gives us our center of rotation. We then of course need the actual point itself, the point that's going to be rotated, and then the angle at which we're going to rotate that. And that's going to return back a point for us with an x and y coordinates, and we're just simply going to use those values to update our current point's x and y coordinates. And after that we're then going to go off and scale them and draw them. But let's have a look at this rotate point function, which is down here a bit. So rotate point. So again, as you've seen, as our input parameters, we've got the origin of rotation, the point itself, and the angle. Now this point of origin, we've seen in our calculations that our formula only work if we're rotating around our origin, our 0, 0 point. So if we want to rotate around any other point, we first of all have to do what's known as translating our point to that origin. So say we wanted to rotate our points around the coordinates 5, 5. What we would need to do is we would need to first of all take 5 away from all of our points coordinates, and that would then in effect make the point 5, 5 our new origin. So in effect we are doing a translation, and that's what's happening here. So we're creating this transposed point, which is basically our new point, which is shifted so that it now has an origin at where we want to rotate around. So that's what's happening here. And again, at the moment, because we're just doing the simple one, both of those origin x and origin y will both be 0, because we already are at our origin. Okay, but that's what's happening in this first bit. We then need to do our calculation. So you can see here that our rotated point x is going to be our transposed point x. So remember, the transposed point is the point which is now centered on our new origin of rotation. And we just simply then fill in the rest of that. So again, we had our x2 equals x1 cos theta minus y1 sine theta, and our y2 point is y1 cos theta plus x1 sine theta. And that gives us our new x and y coordinates for our rotated point. We then need to transpose those back out using our origin. So again, we center around our origin, rotate the point, and then take it back out to where the origin really is in our screen coordinates. And at that point then, we can simply then return our rotated point. So that will be properly rotated around the specified origin. So if we come back up to here, you can see then that in our code, we simply then save that and off we go. So let's have a look and see if that works. So let's save that and run that. Let's make our alien ship just a little bit bigger, and then if I use my arrow keys, we can see now that we can rotate our ship and everything rotates correctly. Now, one of the things we haven't done here is if I keep rotating in a positive direction, we're simply adding more and more onto our values. Now, if I come back out of that and back into our code, that is happening up here when we do our angle increments. Now, our angle increments are, this isn't 0.05 of a degree. All of our angles, and this is the same for most computer languages, most of them work in what are known as radians. So if you're familiar with the idea of degrees, radians is another measure of how big an angle is, but instead of going from 0 to 360 degrees, we're going from 0 to 2 pi radians. So in effect, we are using that idea of the circumference of a circle being 2 pi r, and we now have this idea of 2 pi radians. So it is another way of saying degree. So if you're not familiar with it, don't worry about it, but just remember that we are working with this, we're not working in degrees, we're working in these ideas of radians. So that's why that number there is obviously a little bit, well, quite a lot smaller than a degree. But what it means is that if we keep adding to our angle, eventually we're going to build up quite a large number. So again, 2 pi is about 6.3 in value, but of course if we keep pressing plus, that's going to get bigger and bigger and bigger. Now our code can cope with that, but it would be nice for us to keep our angles in the correct sort of range of values. So what I'm going to do is I'm going to write a little extra function, and I've actually written this down at the bottom here, which is called wrap angle. And what that basically does, it has a look and sees if so we supply it with an angle. And what it's going to do is going to have a check if our angle is greater than 2 pi. So this little bit of code here, so 2 times math.pi, that is 2 pi. So if our angle is greater than 2 pi, 2 pi being the maximum that our radians should take, that's a complete circle, then it just simply takes 2 pi away from it. So in other words, any extra rotations, it just takes them off and gets us back into our 0 to 2 pi range. And similar, if we go to negative angles, so in other words, clockwise angles, then it does exactly the same thing. And it simply returns back the new angle, which has now been scaled back into our 0 to 2 pi range. So up here then, when we do our angle adjustment, we really need to then use our wrap angle function to keep that angle in the correct range. So what we're going to do there is we're going to say our velocity.angle is the wrapped version of itself. Again, that doesn't necessarily make our code any better, but it just stops our angles getting up to really silly values. Eventually, there are limits to all of our variables, which are very large limits. We probably wouldn't ever hit them, but if we were playing a game for a very, very long time and our angles were getting bigger and bigger, it could cause us problems. So it's just good practice to keep our angles within the correct range of sensible values. But that really then is our ship. So we can now draw our vector shape. We know how to specify the points in it. We know how to specify lines. We now know how to draw it on the screen. We now know how to position it anywhere on the screen. We can now scale that shape, and we can now rotate that shape. So really that's everything we need to go ahead now and start building the actual game. And that's what we're going to start in the very next tutorial. We'll start to look at how we model our game elements within our game world and how we then translate that back onto our screen world. And again, as you've seen here, we're starting to already get the hint that I'm modeling in the normal mathematical two-dimensional space. But of course that doesn't actually match up with our screen coordinate system. So we will have to do a bit of work to get that working. But again, we'll cover that in the very next tutorial. Don't forget all of the code I've used here. You can download those plus all of the TIC80 files from my main website on the project page for this. So do check down in the description for that. Don't forget, if you want to keep up to date with these tutorials as I publish them, do make sure you subscribe to the channel and click the notification bell to make sure that you get an email whenever the new lessons are produced. And I hope you're having fun playing with all this code, and I look forward to seeing you in another episode very soon. So, bye for now. Don't forget to visit the course pages for this project. There you'll be able to download the code for this lesson and get lots of extra hints and tips. You'll also get access to all my other programming, electronics and gaming projects. All the links are in the description below. For more games programming, electronics projects and retro gaming, please make sure you like this video, subscribe to my YouTube channel and visit my website.